did now this afternoon. So buffers, we're going to do a little bit on buffers. You probably already heard of or know what buffers are. That's fine. If you need a minute longer, I'll give you a little minute longer. You've probably already heard of buffers. Buffers, you come across them all the time in food tech, in biology, and you probably think they're solutions that maintain pH, right? That's probably what you've been told by your biology teachers, but they're simple folk, aren't they, biology teachers? So we are going to give you a proper definition that you need for chemistry, which is that the solutions that, and I'm going to capitalise to make the point, resist changes to pH on addition of small quantities or small amounts just going to get rid of that, all that stuff in the way. Small amounts of acid or alkali. Small amounts. In other words, I've got a solution. Let's say the buffer is a pH 7 buffer, for argument's sake. Normally they're either acidic or basic buffers, but let's say I've got one that's pH 7 for argument's sake. If I chuck in a bit of acid, the pH will go down a little bit, but only by a little bit. If I chuck in some alkali, the pH will go up a little bit, but only by a little bit. Have you written this down, Sab? You're very fast, okay. Right, so how do they work? And I'm going to focus on, concentrate on acid buffers. I'm going to do it qualitatively and then quantitatively. I bet they'd wish they were in here, not next door. I'm sure that'd be more fun. So acid buffers, you need to know what they're made of and how they work. They're made from a weak acid and the salt of its conjugate base. Okay, we've seen the same old things come up again and again and again. Are you writing this down, Sab? You're going to need to memorise this, right? I want you to know that definition, so you need to write it down. If you're not writing it down, you're just creating work for yourself later on. It's made from a weak acid and the salt of its conjugate base. Okay. And let's use a real example here. Let's use ethanoic acid. And when I say salt of conjugate base, I really just mean the conjugate base. The important thing is the conjugate base is present. So all I'm doing at the moment is I'm explaining. So I'm going to ask you, perhaps once you've written that equation, just to listen while I explain stuff, and then you can catch up with the writing after. This is going to roll definitely into a second lesson, but I want to get to a certain distance through it. Right, so you know that if I've just got the weak acid, where does that equilibrium lie? Point left or point right or point in the middle? Where does that equilibrium lie if I've got a weak acid? There's more weak acid, ethanoic acid. Where's the equilibrium lie? No one's pointing. Point either to that wall or that wall, please. It's a weak acid. A weak acid. Very weak acid. Remember we said that the concentration of a weak acid barely changes at all when it goes into solution. Barely changes at all. Weak acids only release a little bit of H+. So it's like 99% this stuff and hardly any of this stuff, right? But a buffer contains this and a load of this. So what we do is we throw in a load of, to our ethanoic acid solution, we throw in a load of sodium ethanoate. So we add CH3COO the salt of its conjugate base, which we can just get some sodium ethanoate. And that means then that I've got a high concentration of this, because it doesn't dissociate that much because it's only a weak acid. I've got a high concentration of this stuff on the right hand side, which comes from the fact that salts, when they dissolve, dissociate fully into their ions, don't they? When something dissolves, that's what happens. Yeah, it's just a salt dissolving. So I generate in my acid buffer. I've got a load of that stuff and a load of that stuff. Okay. Now we talk about having a reservoir of the weak acid and a reservoir of the conjugate base of that weak acid. Now I just ask you to listen up for a second. So I'm going to talk you through it and then you can catch up. Otherwise you're not listening to the explanation. So if I chuck, remember I said that an acid buffer is something that can resist changes to pH when small amounts of acid or alkali are added. So one of these two things responds and does the work if I chuck in H+, and one of them does the work if I chuck in hydroxide. I want eyes front, please. Are you looking at this, explaining stuff? Eyes front, I'm explaining stuff you've not seen before. So if I chuck in H+, one of these reacts. If I chuck in hydroxide, one of these reacts with it. These are reservoirs. Okay, so which one do you think is going to react with H+ when I chuck it in? That one or that one? A or B? Shout out A or B now. B, A or B. Which one's going to react with H+? A or B? B, yeah, good. So if I chuck in, if H+ is added, you get this reaction taking place, which is the opposite of the one I've just written down. It's really just a forward reaction because it is an equilibrium, but it's so far to the right that H+, can you see, it's just kind of been chomped up because this equilibrium lies to the right. It's just the opposite of that one over there. If hydroxide is added, the other thing reacts, right? And I'm going to do this and then I'm going to give you a chance to write it down. So if hydroxide is added, one of two things can happen, and both you'll see are okay in mark schemes. But the simplest one is to say that the HA reacts with it. If you chuck in hydroxide, the hydroxide will be chopped up and turn into water essentially. So we're taking out most of the H+ and OH that could be added to this buffer system. So that's qualitatively what's going on. I'm going to do an alternative while you're writing this up. The alternative is that the H+ reacts with it, then the equilibrium shifts. So I'm going to put that in brackets at the bottom. It could be that the H+ from this reaction up here reacts and then is replaced by the equilibrium shifting to the right. It's just a Le Chatelier's principle point. So let's go back to thinking about our weak acid, strong alkali graph then for a second. Now we told you yesterday that this region here is the buffer region. So in that buffer region you still haven't used up all of the HA, so there's HA present, and you've created some A- from the addition of the hydroxide. Remember we said that a weak acid buffer, or an acid buffer, is when you've got a mixture of HA and the salt of its conjugate base, which is exactly what we've got in that region there, which is why when we add small amounts of alkali, the pH doesn't change very much, so it's behaving like a buffer. So that's why we've got that narrow, that slow slope upwards. This graph is better than the one that I've drawn, isn't it? This graph is a nice smooth curve. So this is the buffer region here. The pH is going up pretty slowly, okay, compared to what a strong acid, strong alkali graph would be. What is it? I've got a few minutes. Right, so I'm going to add a tiny bit. So first of all, what I've done so far is qualitative, and that's fine. But I'm going to go back to this idea, this equation which I derived a little moment ago. This one here. Write it out again. The pH is equal to pKa plus the log I don't think I'm just trying to explain it properly to you, but I'm really struggling to work out exactly how they're going to ask this. But I want to teach it to you properly, and we'll work backwards from there. So if this is true, the Henson-Hasselbalch equation, which it is, the pH of a buffer, because this is what you've got in a buffer. You've got HA and the salt with conjugate base. Hopefully, you can see that the pH is dependent on the pKa and the concentration of the conjugate base and the concentration of the weak acid. Right, and so when a buffer reacts with either a small amount of acid or alkali, the ratio of HA to A minus doesn't change very much. It's not that that's bothering me, it's just kind of difficult to get right. So I'm going to say that again, it's really important. When you add small amounts of acid or alkali to a buffer, this is the language they use in the specification. So when small quantities, this is what we need to know more than anything else, is when small quantities of H plus and OH minus, or I should say or H minus, are added, the ratio of A minus to HA do not change much. Okay, so pH is dependent on the pKa plus the log of that ratio, A minus to HA. Because of all the stuff we wrote on the previous page, we said that we've got a reservoir of HA, a large reservoir of HA, a large reservoir of A minus. If you've got large reservoirs of those, you chuck in a bit of acid, it gets used up with the HA, chucking a bit of alkali, this gets used up a little bit, but overall the ratio doesn't change very much, and it's a logged number, and you know that logs kind of narrow the range, and so pH doesn't change all that much. That's the key stuff. Now, where we're going to head with this, so I don't think we'll go there today, is we're going to do buffer calculations. And all you've got to do with buffer calculations is plug numbers in, either to this equation, which is what I'm not going to teach you, or you plug numbers into an equation you already know, which is this equation here, and they'll be dead simple. So we'll do that. I will do that next time. You've already got a little bit of work to do for me, so we'll do that next time. And we're also going to talk about basic buffers, which are unsurprisingly a weak base and its conjugate acid. We'll talk a little bit also about how the buffers are made, either by chucking in the salt or by adding in alkali, as we've just done there. So that's what we're not stopping the lesson, stopping this bit of the lesson. I'm going to do a bit of quizzing of hybridization for the last 4 minutes.